Greetings. In the first part of this video, I managed to introduce you to the original refrigeration cycle, where it consisted of a compressor, condenser, throttling valve, and an evaporator, which just did the four basic actions that we required for extracting heat from a colder reservoir and then delivering it to a warmer reservoir. Then I added an addition to that cycle, which was just a heat exchanger, where it used the heat still available out of the condenser in this heat exchanger to warm the saturated vapor going out of the evaporator so that we would just be sure that no liquid droplets would enter the compressor and destroy it. Please note that a compressor in, say, a refrigerator, it works for, say, 20-25 years. And if it is to receive some droplets, then surely those droplets would ruin the compressor and it wouldn't last that long. Usually, refrigerations and refrigerators are expected to work for very long periods. Now, once we knew the two basic pressure values that our system was working on it, what we did was to go to the tables and read the key values. In fact, we read the enthalpy and entropy of saturated liquid and saturated vapor for both our pressure lines. Then we attempted to fill in a table which was basically telling us what the properties at each point in our cycle, whether we look at it in this diagram or we look at it in this diagram, would have. And we managed to fill in quite a number of points. The points that are left are point 5, 1, and 2. These are the 3 points that we have one property out of them, and we still require a second property. So, point 5 is fairly simple because it's just after a throttling process, and we well know from our throttling lessons that enthalpy remains constant for the throttling process. And so we may write that H4 equals H5. And once we know that H4 and H5 are equal, we know H4 to be 93.58 kilojoule per kilogram, and therefore we may also know H5, which is another knowledge that we need here. It is H5 that we needed, and its value would be 93.58 kilojoule per kilogram. This is the enthalpy for point 5. We may also calculate the entropy for point 5 just by calculating first the quality, and then after the knowledge of quality, we could also calculate entropy for point 5. X5 is H5 minus HF divided by HFG on this line. Okay, I mean on this line. And we have all the values. It is 93.58 minus 38.43 and divided by 200.03. And the outcome for x5 would be 0.268. Now that we know the quality at point 5, it would be very easy to calculate S5. And S5 is 0.3642 kilojoule per kilogram. And therefore, we can also fill another box in this table, and this is S5, and it is 0.3642 kilojoule per kilogram. We might need some of these values in this problem or not, but these are the basic values. Assume that if you want to do an exercise study on this problem, then you would need all the enthalpy and entropy for every point. So once you have calculated all these values, then it would be very easy to do all sorts of post calculations for all cycle properties or do an exercise study on individual components or the whole cycle. Now, we are only left the points 1 and 2, and point 1 is the next one that we may calculate it since we have one heat exchanger here, and we could just write the first law equations for this heat exchanger, and it's a good practice just to remember once we have come to it, because you see this heat exchanger here, it receives its heat from this part. So one step that we always have to take for this cycle is to calculate, write down, simplify the first law, second law, and equation, or all our equations for this cycle. And it's simple to just write down the equations, because since the cycle is steady state, you might write 0 equals m dot I minus m dot E, and this is valid for all components. Just for example, if you want to write it for condenser, you may put I as 2 and E as 3, and the equation would be valid. If you wanted to write it for the compressor, I would be 1 and E would be 2. So this is just general for all components. The first law would be 0 equals m dot I hi. The changes in velocity and elevation are just minimum, are just very little for such cycles, and are usually ignored, so that wouldn't matter. Minus m dot he and plus q minus w. And also we have to multiply this by m dot, which is either m dot I or m dot E. Divide everything by m dot, and 0 would be hi minus he plus q minus w. Now, how do we use this equation? If we have a compressor, then for the compressor, we do work, and heat transfer is 0. So we have work and no heat transfer. If we write it down for condenser or evaporation, for evaporator, there is no work, but there is heat transfer. So work is 0 and there is heat transfer. If we write it for throttling valve, there is no work and there is no heat transfer, so HI equals HE. And if we write it for this heat exchanger, there are 2 inlets, 2 outlets, no work, no heat transfer. Similar way of simplifying the second law, it would be Si minus Se plus Q over Tb and plus S dot Gen over M dot. Uh, Still, if the compressor is adiabatic, this one vanishes. The condenser and evaporator have heat transfer, so there is heat transfer for both of them, and there is change of entropy for both of them. The throttling valve, of course, is irreversible, so as such and would be present for it. It's adiabatic, this one vanishes. And so we can simplify, we can use just what we have learned in our lectures on first law and second law. We have to just apply them here, and I won't just go to the detail of doing them one by one. You could watch my previous videos just to learn how to simplify the thermodynamic laws for each individual item. Now that we are working on the cycle, then we have to just uh, use our previous knowledge and jump to our final results. Well, as far as the heat transfer is concerned, the heat exchanger, for the heat exchanger, we use this equation, and there's no heat transfer to the outside, there is no work, but there are 2 inlets and there are 2 exits. But, so we write down the first law for the heat exchanger. First law for the heat exchanger. And that is 0 equals, well, on one side, H3 is in, H4 is out, so H3 minus H4 plus, and on the other side, it is 6 and 1, and 6 enters, 1 exits, so it is H6 minus H1, and the only unknown in this equation is H1. So H1 would equal H3 minus H4 and plus H6. We have all enthalpies for points 3, 4, and 6, and therefore this would equal 101.61 minus 93.58 and loss 244.46, and H1 would be 252.49 kilojoule per kilogram. This is the value for H1, and I should write it here. 252.49 kilojoule per kilogram is the value for H1. We don't know its temperature and its entropy. we expect H1 to be superheat, so we have to move to the superheat table for R134A and see what we can learn from that table. Well, let's move to the superheat table for the R134A, and as you see, for 200 kilopascals, zero point 0.2 megapascals, the saturation temperature, as we know, it is minus 10.09, and the knowledge we have is that H, we just calculated H, to be 252.49. 252.49 is just very, very close to 0 degrees centigrade, and it is between 0 and minus 10. It is between 0 and minus 10. So we could do an interpolation. It is very close to 0, we expect, but I would just read these values, temperature, enthalpy, and entropy, put them in a table, do the interpolation, and calculate the real values. These are our values from the superheat table for 200 megapascals. The pressure here is 200 megapascals for the values in this table. And what we know for point 1 is its enthalpy, which is 252.49. And if we use this value to interpolate between 0 and 10, the temperature would be minus 0.658, which is very close to 0, as I just mentioned. And the entropy would be 0.9677. So these are the two unknown values for us that we needed here for point 1. We now know that the temperature is 0.658 and the entropy 0.9677. 0.9677 is the entropy for point 1, is the entropy for point 1, and the enthalpy we just calculated to be 252.47. So as far as point 1 is concerned, we now have all the required knowledge. How do we go to point 2? We know that the compressor is adiabatic and reversible. If there is a heat transfer, then we must be told the path. I mean, we have to know some way the path. Either the problem has to tell us the temperature at point 2, which of course is one knowledge. We know the pressure, we know the temperature, so we could calculate or read all the properties. Or it should tell us the isentropic efficiency of the compressor. So we would calculate the isentropic process and then use the efficiency to calculate the real process. Or it should tell us give us some idea about the heat transfer, and therefore, once we know the heat transfer, we would insert that value into this equation and would calculate the work from inlet or outlet conditions. So somehow there should be some knowledge of whatever that happens inside that compressor. For the present problem, it tells us that the compressor is adiabatic and reversible. So to calculate the compressor, once it is adiabatic and reversible, we know that it's adiabatic, so this term vanishes. It's reversible, so this term also would vanish, and therefore the entropy would be the same for compressor inlet and exit. That means that the entropy at point 2 would be the same as entropy at point 1. And what we do is just to insert this value 0.9677 for entropy at point 2. Now we know two information for the entropy at point 2 and the pressure at point 2. So for 900 kilopascals, and this one is kilopascal as well. It is zero point 0.2 megapascal, but 200 kilopascal, it is zero point 0.2. We just know the entropy for it. Okay, we know the entropy for 0.2. That is 0.9677. We know the pressure, and now we have to read temperature and enthalpy from the table. And if we move to the table and for 900 kilopascals, which is 0.9 megapascal, our entropy is 0.9677, which is somewhere between this one. 9677 is just above 50 degrees C. This line, I mean, just above 50 degrees C and far below 60 degrees C. So our temperature we expect to be very close to 50 degrees C for all good approximation. I think we wouldn't have anything more than a degree centigrade difference between these 2 points. But what I would do is to write down the values up and down. These values, the values for 50 and 60 in a table, and interpolate it just to make sure that we are doing the right thing. But please note that for all intents and purposes, there won't be any any accuracy that we would gain from just losing about half a degree. Now, if the temperature is 50 degrees C, and I'm using the titles here, the enthalpy is 284.77, and the entropy is 0.9660. And for 60 degrees C, the enthalpy is 295.13, and the entropy is 0.9976. And once we know this value, we could interpolate it for enthalpy and temperature, and enthalpy would be 285.32, and the temperature would be 50.5 degrees C, and therefore we can complete the final values in our table, the final unknowns. The temperature is 50.5 for point 2. You see the temperature for point 3, this line was 35. We expected 2 to be At higher temperature, it is 50 degrees C, and the enthalpy is 285.32. And the green numbers are what we have calculated, and the or interpolated, and the blue ones are those that we directly read them from the tables. So we now have all the knowledge of different points of our cycle. For every point in our cycle, we have the enthalpy and the entropy. We have calculated the properties. We have written down the equations and simplified our governing equations. We have drawn our diagram, a free body diagram, and a TS diagram. So we have basically done all the steps that we require for calculating. Now we have to do the final step. We have to take the final step and do the cycle calculation and see what the problem has asked from us. It is a very good practice at this stage to look again at the first law of thermodynamics, and we learned that for different processes in our cycle, we could write this equation, and it is either heat transfer or work for different components, and any of them, either heat transfer or work, would equal inlet enthalpy and exit enthalpy. It would be a very good practice to just draw another table, which I have done here, and write down Hi minus He for individual processes 1, 2, 2, 3, all to the 6, 1. So this is all the processes in the cycle. You see, unlike this table where I concentrated on point properties, this table tells us about the process properties. And the process properties, at least for the time being, is Q, W, and delta H for the first law. If we wish to do a second law analysis, then we would have to add, we have Q, we would have to add the entropy generation and see what that tells us. But for the time being, we could easily calculate Hi minus He for each process of the cycle, and process 1, 2 is the, I will just put our cycle here. For process 1, 2, Hi minus He, and please remember and note these signs, because if you don't care for the sign convention, then you would have problem at the end. It is minus 32.83. For process 2, 3, in the condenser, it is 183.71. For process 3, 4, it is 8.03. For process 4, 5, process 4, 5 is in the throttling valve, and delta H is 0. Process 5, 6 is in the evaporator, and from the table, this would be minus 150.88. And for finally, for process 6, 1 is heat transfer, and it is minus 8.03. You see, process 3, 4 and process 6, 1 are both inside this heat exchanger. One absorbs it, one rejects it. So at the end of the day, they equal. Now, Once we have this table, let's look at the first law, and Hi minus He for process 1, 2 in the process 1, 2 is in the compressor. Perhaps it would pay to have this diagram here. Process 1, 2 is in compressor. There is no heat transfer, so this is 0. Therefore, work equals 3, 2. Note that work would equal Hi minus He, so there would be no change of sign here, and it would be minus 32.83. For process 2, 3, there is no work, work is 0, and heat transfer would be the negative sign of Hi minus He, so it would be minus 183.71. For process 3, 4, there is no work, it's only heat transfer, and Q would be minus 8.03. You see, all Q values would be negative of Hi minus He. All work values would be the same. Process 4, 5 is in the throttling valve, and there is no heat transfer, there is no work. Process 5, 6 is in the evaporator, and there is no work, and the heat transfer would be 150.88. And here in 6.1, work is 0 and heat transfer is 8.03. Just to check that we have done all our calculations up to now, we have done them correctly. We just add all these values and it would be minus 32.83. Add all work values and it would be minus 32.83, and all delta H should be 0 for the cycle. In fact, what you would calculate here is minus 0.01, which is good enough. Some approximations have resulted in just 1% error in the cycle calculation for enthalpy. Now, once we have these values, now we could see what cycle properties we could calculate. We now have all process properties, which is heat transfer and work. Now, let's return here and define COP for our coefficient of performance for the refrigeration cycle. And as we know it, it is the heat transferred from the cold reservoir to the work done. What we have gained is that we have cooled this reservoir and then the work we have done. So it would be 150.88. That is the heat transfer between 0.5 and 6 divided by work, which is process 1, 2, and that would be 32.83, and the outcome is 4.60. This is the heat transfer. This is the heat transfer divided by work, which is the coefficient of performance for the refrigeration cycle. Now, if this was a heat pump and our intention was to warm this rubber reservoir, then we would have a different COP for the heat pump, and that would be the temperature, the heat transfer we have gained from the warmer reservoir, which is 183.71 divided by 32.83, and that is 5.60. You see, this value is Q56. This is Q56. This is W12, and this is Q23, and that is W12, depending on whether we wish to warm a warmer reservoir, then it would be a heat pump, and the coefficient of performance would be calculated this way. Or we wanted to cool a cooler reservoir, and the coefficient of performance would be calculated. Q56 would be what we Q56 would be what we gained, and what we had done for it was work from 1 to 2. You see, they are 1 away from each other, and the reason is because if we write down the first law of thermodynamics for the whole cycle, the difference between these two values is work. I mean, you could easily prove that you could write Q56 divided by W12 plus W12 divided by W12 equals Q23 divided by W12. This could be easily shown, and the outcome is just a 1 difference between coefficient of performance of each of these two um, cycles. Whether this is the same cycle, just our targets would be different. Whether it is a heat pump or it is a refrigeration cycle. Well, thank you very much for watching, and cheers.